Welcome back to Math and Beats. This time it's math, and we're going to talk about some more logic, conversations. Specifically, we're going to talk about the converse, the inverse, and a little bit more on the contrapositive of a statement. Here we go. All right, to begin with, we're just going to start with an example. This example wants us to construct a truth table for this statement right here. If Q, then P. And then we want to talk about whether or not it's logically equivalent to if P, then Q. So are these the same? Let's go ahead and start our truth table. See, we got a column for P, Q, if P, then Q, just so we see it. And then finally, if Q, then P. So we're always going to start it with true, true for P and Q. True, then false, false, true, and false and false, the four different combinations. And then we already know what the logic table for if P, then Q is. It's true if they're both true. And then it's false if a true statement implies a false statement. Otherwise, it's going to be true. Now we go the backwards direction. If Q, then P. Let's go in this way for that last column. So if Q is true, P, then P is true. That's true. Second row. False, then true. That is true. True, then false is false. And false, then false is true. So as we can see, as we compare these two columns right here, these two statements are not logically equivalent. So we should write that down. If Q, then P is not logically equivalent to if P, then Q. Why do we care about that? Because, it's kind of like the backwards of the original statement, if Q, then P. And since they're not logically equivalent, we can't always say they're the same. So in general, those two things are not the same. And to be a little more specific, this statement we just looked at, if Q, then P, actually has a name associated with it. It is called the converse, all stars, of if P, then Q. So we have a name for that. If Q, then P is called the converse of the original statement, if P, then Q, and those two statements are not logically equivalent to each other. So that's a new vocabulary. Another one that we're going to look at right now, another important statement, is called the inverse of if P, then Q. And that is this statement right here, if not P, then not Q. That is the inverse of if P, then Q. So we want to look at the truth table of this one as well, and then make some kind of conclusion based on the final result that we get. So again, we're going to start with the different types of forms we can get for P and Q. True and true, true and false, false, true, and false, false. Now we're going to have two columns here where we negate the P and the Q so we can discuss the inverse of the statement. So look at the P's over there. The trues become falses. The falses become trues. And then the Q's, negating those, again, the trues become falses and the falses become trues. And then we got a column here for the original statement, if P, then Q, just so we can compare it to the last column. So that is true, false, true, true. So finally, we're going to look at if not P, then not Q. All right, these two columns right here for that last column. False, then false. That's true. False, then true. true. True then false is false. True then true is true. So then, again, we compare these two columns right there, and we should note, again, that these two statements, the inverse and the original statement, are not logically equivalent to each other. So write that down. If P, then Q is not logically equivalent to its inverse. If P, then not Q. So they're not the same in general. But another thing that we should notice, go back to the last one. We look at the converse. If Q, then P, right over there. True, true, false, true, using the same setup for P and Q that we started with. And then in the inverse, true, true, false, true as well. So another conclusion we can make is that if Q, then P, the converse, this actually is logically equivalent to the inverse, not P, then not Q. And that's not a coincidence, because if you recall from the previous video, these two statements are actually contrapositives of each other. And we already know that a statement and its contrapositive are always logically equivalent to each other. So those three different types of statements, being specific, the converse, the inverse, and the contrapositive, are all different forms of an original statement that we often like to investigate, look at its truth value in a mathematical setting. And we know that a statement and its contrapositive are logically equivalent to each other. A statement and a converse not logically equivalent to each other. A statement is inverse not logically equivalent to each other, but the converse and the inverse of an original statement are indeed logically equivalent to each other. Okay, so that's some of the important vocabulary and the results we got. One more example before we end this short video. Here's an example where we're just going to write the converse, the inverse, and the contrapositive of the following statement, which I'm about to show you, and then also talk about the truth value for each of these statements. So to begin with, what is the statement we're interested in? Here it is, boxed in blue. If it is snowing, then the temperature outside is less than 100 degrees Fahrenheit. Now that statement itself, we could presume to be true. I don't know of any circumstance where it has been snowing and it has been 100 degrees Fahrenheit or more outside. That would be pretty crazy. So I think it's safe to say that's a true statement. All right, to set up, to write each of these statements that we're interested in, the converse, inverse, and contrapositive of that boxed in blue statement above, let's let P be the first part, the hypothesis. It is snowing. And let's let Q be the statement, which is the conclusion. The temperature outside is less than 100 degrees Fahrenheit. So that's P, and that's Q. And of course, the original statement that we have above, if it is snowing, if P, then temperature outside is less than 100 degrees Fahrenheit. Q. So now we'll manipulate these using converse, inverse, and contrapositive and look at the truth value. We already know the contrapositive should also be true because it should have the same truth value as the original statement. So here is the contrapositive. We reverse the order of the statements and negate each. If not Q, then not P, the contrapositive. And in words that would say, if the temperature outside is greater than or equal to 100 degrees Fahrenheit, then it is not snowing. And that is presumed to be true based on our, I guess, inductive observations about reality so far. What about the converse? If Q, then P. right here. If the temperature outside is less than 100 degrees Fahrenheit, that's the Q right there, Q, then it is snowing, P. So if the temperature outside is less than 100 degrees Fahrenheit, then it's snowing. That is not necessarily true, because it could be 99 degrees outside Fahrenheit, and it's quite reasonable to think that it's not going to be snowing. Finally, the inverse. If not P, then not Q. So if it is not snowing, there's your not P, then the temperature outside is greater than or equal to 100 degrees Fahrenheit, the not Q statement. Well, that's also false, because just because it's not snowing outside doesn't mean the temperature has to be 100 degrees Fahrenheit or more. Again, that could be 98 degrees outside if it's not snowing some. So that's also false. And so that's just a little example to see the symbols at work in some real world context of a sentence. And that is it for the video. So the main parts of this video, just a little refresher on the contrapositive. We discussed the converse and the inverse of an original statement and talked about their truth values. And so really we have a lot of vocabulary now and some techniques, inductive and deductive reasoning techniques, to get us through and actually proving some more statements in mathematics. We're going to look at a few more techniques of proof, specifically ones that involve existential quantifiers, and then after that we'll really have a nice toolbox of tools to use to go and prove some mathematical statements. So that's it for the video. Stay tuned for the next video, because it's going to be more logic and math. All right, Matt and Bates, peace out.